Hi everyone. I'm going to talk about measurement of water content, and we will discuss a few common methods that are used to measure the water content of porous media. Also, I will talk about the concept of the specific storage, a storage coefficient, and a specific yield in aquifer. Okay, and this is a part of chapter 2 of our course on groundwater hydrology. Okay, so let me read it from here. That is, the determination of the water content of soils is of great importance to describe various hydrologic processes. I believe you all agree with me that it is important to know how much water we have in soil to be able to describe various hydrological processes like water evaporation, soil salinization, microbial activities, irrigation, and so on. So it's important to have an accurate kind of measurement of the amount of the available water. Okay, so and there are several methods to do so, to measure the water content, and today I'm going to discuss a few common methods. First, I wanted to review for you very quickly the definition of the water content. If you remember from the previous lectures that we defined gravimetric water content and volumetric water content. Okay, and for the gravimetric water content, we said theta m is equal to mass of wet soil minus mass of dry soil, that gives you the mass of the water, divided by mass of the oven dry soil or the solid phase. Okay, and so that's the way you determine the gravimetric water content. And for the volumetric water content, you divide the volume of water by total volume of the soil. In other words, so in other words, instead of volume of water, I write mass of water divided by density of water, okay, and total volume of soil. So you have the soil basically sample volume. And we derived this equation in the previous lectures, that is the theta V, volumetric water content, is the theta M, that is the gravimetric water content, times the bulk density rho B divided by rho W. Okay, so you knew already these definitions from previous lectures. Okay, so in my opinion, one of the simplest yet one of the most accurate method to determine water content is simply just measuring the weight of the wet soil. Okay, so you have here the wet soil, you put it on a balance, you have the mass here, and then you put this one in the oven. Okay, and then you dry the soil, and at the end you measure the mass of the dry oven dry soil here. Okay, and now you can simply use this formula to calculate the average water content of this soil sample. That is the mass of the wet soil, you have it from here, right? And mass of the oven dry soil, you have it from here, right? And divided by the mass of the oven dry soil, that is again you have it from you have it from here. Okay, so then you can calculate the theta m by that. And then when you have the mass of the water, that is the difference between wet minus dry, you can simply as well calculate the theta v, that is mass of water divided by density of water. You know the density of water, and that gives you the volume of water. Then you divide that by the volume of your basically soil sample, and that gives you the volumetric water content. As I said, this is probably one of the simplest yet one of the most accurate ways of determining water content. Okay, there is another method that is based on like time domain reflectometry, or simply TDR. And time domain reflectometry is another technique for measurement of volumetric water content using electromagnetic waves propagating along embedded waveguides. Okay, and that's kind of a picture of a TDR, a typical TDR sensor that you get, and that is basically the measurement is based on the propagation velocity, the wave propagation velocity along waveguides, and which is basically these rods here. Okay, these rods here, right? So you will see in a second that how does it work, but I wanted to first give you a little bit of like a theoretical background. That is the propagation velocity v of an electromagnetic field along a waveguide of length L embedded in wet soil is affected significantly by the soil dielectric constant epsilon b. So soil dielectric constant is presented by epsilon b that varies with water content. Okay, so basically we're saying that the propagation velocity of the wave along this waveguide that is embedded in soil is a function of the is affected by the soil dielectric constant. Okay, So, in other words, there's an equation here that is the propagation velocity, that is v equal to 2L divided by t. Why do we say 2L here? Because the wave basically goes through here, through this rod, goes here and then come back again. So that will be 2L. Okay. So the propagation velocity 2L divided by t is affected by the bulk dielectric constant. According to epsilon b, that is the dielectric constant, is equal to c, that is the speed of light, divided by v, that's the propagation velocity squared. Okay, and instead of v here, instead of v, I simply write 2L divided by t. And if I put 2L divided by t, you can rewrite this equation as epsilon b is equal to c, that is the speed of light, t, that is time, divided by 2L. L is the length of the rod with the power of 2. Okay, this equation simply says, it states that the dielectric constant of a medium is the ratio squared of propagation velocity in vacuum, okay, relative to that in the medium. Okay, so that's the time domain reflectometry, TDR. So now, let's say with the sensor, you have the epsilon b, okay, you have the dielectric constant. Okay, there are two ways that you can convert this dielectric constant to water content. Remember, we wanted to calculate the water content, and we need to find a way to convert this dielectric constant to water content. So there are two common approaches to do that. One is the empirical equation known as a Topps equation. We will discuss it in a second. And then another one is a more physically based equation. And the empirical or calibration relationship is that a kind of a third order polynomial proposed by Topps et al. In 1980, the reference of this paper here, relating dielectric constant to water content. Okay, and so this is theta v, that is the water content, and there is this third order equation here, and you see here you have the epsilon b here, right? So you measure the epsilon b, you plug it here, and then you get the volumetric water content. This is an empirical equation. Okay, and so yeah, it's relatively straightforward to use that. You measure the dielectric constant, you plug it in this equation, you get the water content, and that is called empirical equation, known as the Topps equation, to calculate water content based on TDR measurement. The other one is a physically based equation, and that basically is based on the Maxwell basically was among the first to employ a physically based dielectric mixing model. Okay, that's based on the Maxwell the dielectric mixing model that incorporates volume fractions and geometrical arrangement of constituents to predict bulk dielectric constant of a mixture. Okay, so when you're dealing with like a soil that you wanted to measure the water content, so you're dealing with you have air in the system, you have water in the system, and you have solid phase in the system. Okay, so so here the dielectric constant of this medium, this kind of the effective dielectric constant of this medium that includes water, oil, and water, air, and solid phase is equal to theta v, that's the water content, times epsilon b. Epsilon b is the dielectric constant of water with the power of beta, plus 1 minus epsilon. Epsilon here is porosity of your soil, times epsilon s, that is the dielectric constant of the solid phase or soil power or sand particles, soil particles, okay, with the power of beta, plus epsilon, that is the porosity, minus theta v, that is the unknown here. We wanted to calculate the water content, times epsilon a, which is the dielectric constant of air with the power of beta, and everything again with the power of 1 divided by beta. As I already explained, epsilon s, epsilon w, and epsilon a are the dielectric constant of solid, liquid, and gas phases respectively. Epsilon is the porosity, and beta is related to the applied electromagnetic field. Okay, and so in our case it is a known parameter. I will show you in the next slide. But you can see here, if you look at this equation, you'll see here you have all these parameters except the theta v. Okay, assuming you have the porosity of your sample, you have all the parameters except the theta v, and therefore you can calculate the theta v as a function of the other parameters. Okay, so basically that was the equation. You can rearrange this equation. This is a simple algebra. You can express theta v as a function of the other parameters, and the mixing model can be simplified using, for our application that we're measuring water in soil, it's not that bad if we assume beta value is equal to 0.5. So we assume a constant value for beta 0.5, and also the dielectric constant of the water, we know it's 81. The solid phase for soil, we assume it's 4, and for the dielectric constant of air is 1. So if you plug these constant values, that is 81, 4, 1, and 0.5 into this equation, you will end up with this equation here that relates the water content to the dielectric constant that is measured here and porosity of your sample. Okay, and that is the physically based model that is used to convert the dielectric constant, soil dielectric constant, to the water content. Okay, so you can compare the performance. You can compare the performance of this model. So that is the bulk dielectric constant versus volumetric water content, and the green is the mixing model. Okay, and the blue one is the approximation, TOPS approximation, which is an empirical equation. Okay, as you can see here, the TOPS model works quite well for the water content, less water content range, less than, I would say, 50%, okay, which covers the entire range of interest in most environmental applications. However, as you can see here, there is a lot of discrepancy between the blue and the green line here. However, it fails for water content higher than 50%, and also for soil with high organic matter content. Okay, so that was about the physically based dielectric mixing models and its performance compared to the TOPS equation, or better to say the performance of the TOPS equation, the empirical equation, with respect to the physically based dielectric mixing model. Okay, so there's a simple example here. That is, what is dielectric constant of a soil sample having theta v 20%, rho s 2,650 kilogram per cubic meter, and bulk density of 1378 kilogram per cubic meter. Okay, so you have the theta v, you have the bulk density, and you have the particle density, and the question is to calculate estimate the dielectric constant. So to do that, first you need to calculate the porosity of your sample, and you know from the previous lectures that we have an equation relating the particle density, bulk density to the porosity, that is if epsilon is equal to 1 minus rho b divided by rho s, which is equal to 1 minus, instead of rho b here I put 1378, and instead of rho s here I put 2650, and if you do the calculation, you'll end up 48%. So 0.48 is the porosity of your sample. And now you can use this equation, okay, to calculate your bulk, the dielectric constant. And for that, you already have the theta v, okay, that is given in the question, 20%. You have the epsilon v w, that is 81. You have the epsilon s for solid phase, that is 4. And you have the epsilon a, that is 1 for air, okay. And epsilon you already calculated, that is 48%. And beta, as if you remember in the previous slide, we said that here we said that the beta in our application is equal to 0.5. So you just plug here 0.5, and if you do the calculation, you'll end up dielectric constant of epsilon b will be equal to 9.73. Okay, and that's the solution to this example. So I decided I'd like to discuss some more, I would call it, I don't know, like a more modern technique to measure that can be as well used to measure the water content. So one of them is Neutron radiography, and which is a non-invasive method for mapping of water content distribution at high spatial and temporal resolution if necessary, based on the neutron transmission. So the key here is that the neutron is very sensitive to the hydrogen atom, okay? And hydrogen atom, as you know, is a part of the water molecule. Okay, so what happens here is that using a two-dimensional neutron camera, Okay, the image captured is a gray level image where the gray level of each pixel is proportional to the amount of water within that pixel. So you have basically a 2D sample or quasi 2D sample. You put it in front of the neutron. Neutron goes through this sample and it is attenuated because of the hydrogen atom of the water molecule. And there is a detector behind your sample, and that will basically, this attenuation will be detected by that detector. Okay, and then you can relay the intensity of the neutron, basically, neutron beam to the water content of your sample. So this is the equation here, that is the Beer's law, that the intensity I of a neutron beam passing through a porous media of thickness ds, is the thickness of the porous media, with glass the walls of thickness dg. So let's say if your porous material is in a glass column and the neutron goes through that, you can relate this intensity neutron in the intensity of the neutron beam to the water content via this equation. So I and I naught is the basically neutron beam intensity before passing through the sample porous media is I naught, and after passing through the sample is I, and dg is the thickness of your porous media, and ds is the thickness of your glass wall, epsilon is the porosity, theta here is the water content that we are interested in, and mu g, mu m, and mu w are basically the neutron attenuation coefficient. For basically mu g is for glass, mu m is for porous media, and mu w is for water. Okay, and here is an example that is basically our own research result. We published it in 2008 in Water Resources Research. So I think perhaps it's easier to explain via this picture how it works. So this is my soil sample here, as you can see here, that I had a glass container packed with I guess sand particles saturated with water. We were interested in investigating the evaporation process such as through such a sample. So the column was there, basically left for evaporation, and then there was the neutron beam, basic, as you can see here, this part going through this sample. I don't know, every few minutes, basically, we recorded a picture from this the drawing sample, and this picture here is a typical example or typical output of this the instrument, basically. And here the very dark color here, the dark gray color here is the saturated phase, the zone or the region saturated with water, and the light gray is the unsaturated zone. Okay, and as you can see here in the saturated zone, so since it was saturated with fully basically filled by water, you have more attenuation. Okay, and so in each this is a digitalized image, and basically it has a lot of pixel, basically, right? And in each pixel has a gray value, and that gray value of that picture you can relate it to the water content. And this is, for example, an example of the result you can get from such an image. That is the depths below the surface. So here is the surface of your sample, and that's the depths below the surface. So you go down this way, and that's the water content. Okay, and here basically we calculated the water content on each basically level below the surface and averaged it, and now here and the result present in this figure. You see here two curves, like a dash curve and dash line and solid line. That is that indicates the different boundary conditions in our experiment. In one case, as you can see here, we had a hair dryer that was close to the sample and caused high level of water evaporation, so we named it high. And in another case, this hair dryer was a bit away from the soil sample or drawing sand sample, and the potential evaporation was less, so we call it low here. And the number here basically indicates the depth of the drawing front, and the drawing front was defined as the interface between the saturated and unsaturated zone. And here in this figure, basically somewhere like here, you see the interface between this dark gray and the light gray is somehow this is called the drawing front. And yeah, so we can let's say if necessary, you can continue this experiment, let's say, I don't know, for 24 hours or 48 hours, and then every few minutes you take the picture. So the resolution of these pictures, I guess in this particular case, I think it was something in the order of maybe 100 micron, and so with a very high resolution, a spatial resolution and temporal resolution, because you can take the picture every few minutes, so you can get the dynamics of the water content distribution distribution through this sample. So neutron radiography is one of the, I consider as one of the modern techniques to measure water content. Another one is the X-ray tomography. Okay, this is another non-destructive technique capable of visualizing inside of 3D solid objects, in our case soil sample, which provides detailed information about phase distribution and geometries in 3D. Okay, and this is actually very similar. The way it works, the X-ray computed tomography is based on the similar technology to that used by physicians when they image broken bone. Okay, the main difference is, the only difference is that there they take only one 2D X-ray image or the so-called radiograph, but in our case we get lots of radiographs are taken as the object rotates. So you have the object in front of your beam, and then it slowly rotates, and from each angle you take one radiograph. Okay, and this series of radiographs eventually will be used ultimately will be used to reconstruct a 3D sample. And then from that, then in your 3D sample, then you can calculate the different phases, quantify different phases. And in our case, will be solid phase and liquid phase and gas phase. Okay, and here I have some examples. This is a picture of me when I was much younger. And here I'm running some experiment with X-ray, with synchrotron X-ray tomography. And to calculate basically the water content distribution, or better to say that to quantify the dynamics of the evaporation from porous media and solute transport. So so here, this is the sample I have, and I put this coin here just to give you an idea about the scale I'm talking about. So this is my, let's say, soil sample or sand column. I fill it with sand particles saturated with water or salty water if necessary, and let it to dry. And then I take the picture from this system. I wanted to know how the phase distribution evolves during evaporation in 3D. And this is a typical cross section. This is a 2D cross section that you get after reconstruction of the radiographs, and then you can segment this to blue and so in this case it is the saturated condition. You see here the blue color is the liquid phase, and the solid phase is the grain, sand grain. You can also, when your experiment continues, of course, part of the pores will be invaded by air, and then you can segment this image. You get the blue color here is the liquid phase, white color is the air phase, black color is the solid phase, and then you can, for example, reconstruct only the solid phase if necessary here, so you have the detailed information of the phase distribution. Okay, and these results were published in a couple of papers in 2010, 2012, 2018. So if you're interested, yeah, please feel free to visit our website and look into the papers for more detail. Okay. And so yeah, this is again another example. So here, this is this data was measured by synchrotron X-ray tomography. You see here, I can get now the detailed information in 3D about the sand arrangement, the particle arrangement. Here, I'm just showing you the liquid phase distribution. Okay, liquid phase distribution. We removed the solid phase. We wanted just to highlight how the liquid phase morphology and distribution look like in 3D. And now, if for example, we are interested, let's say, in calculation of the water content, we can using image analysis tools and techniques, we can calculate the volume of this liquid. Okay, so X-ray tomography is another, in my opinion, modern technique that can be used to measure water content. Okay. And so there are only 3 more definitions here, as I mentioned at the beginning, about the specific storage, a storage coefficient, and a specific yield. And then after that, chapter 2 of this course will be concluded. Okay, so let's first look into the specific storage. That is the degree of saturation for groundwater flow is always unity, and the volume of water stored in a saturated porous medium, because it is saturated porous medium, all the pores are filled by liquid, and therefore the volume of the water will be equal to the volume of your aquifer times the porosity. Okay, because you're dealing with a saturated porous medium. Okay, and when so water recharge or water recharge to or discharge from an aquifer represent a change in the water storage volume within the aquifer. Okay, when you take the water out or when you basically recharge the aquifer, basically you're modifying the water storage volume. Okay, when the hydraulic head within an aquifer with the thickness of H decreases or increases, okay, water is released. So when the hydraulic head decreases, water is released, or when the hydraulic head increases, water or taken into a storage. Okay, when the hydraulic head increases, you're basically adding water to your aquifer or recharging it. But when the hydraulic head basically is decreases, that means you're taking the water out of this, or water is released from the aquifer. Okay, so the definition of the storage, the specific storage is defined as the volume of water. The volume of water that a unit volume of aquifer releases or taken up, okay, that can as well take or takes up, that can as well that is as well correct, in response to a unit decrease or increase in pressure head is called a specific storage, represented by the SS of the aquifer. So basically, S, that is 1 divided by L, that's the dimension, is the volume of water released from a storage, okay, divided by the volume of aquifer times decrease in pressure head. Or you can define it as volume of water taken into storage divided by volume of aquifer times increase in pressure head. Okay, so that is the definition. That's the definition of a specific storage. Okay, so there is another definition here that is called a storage coefficient. And a storage coefficient or a storativity is defined as the volume of water, as defined as the volume of water that an aquifer releases from or taken into a storage per unit surface area of aquifer per unit change in hydraulic head. So when you look at this definition, when you compare it to the previous one, it's quite similar. The only difference is in a specific storage, you had per volume of aquifer, while for a storage coefficient, you have per surface area of the aquifer, okay? And that is called a storage coefficient. That is denoted by S. So S is equal to volume of water released from storage divided by surface area of aquifer times decrease in pressure head, or volume of water taken into storage divided by surface area of aquifer times increase in pressure. And then when you compare this equation, this definition, with the previous one here, you can see here, if you multiply this SS by the thickness of your aquifer, by the thickness of your aquifer, because this volume is equal to thickness times area, right? So if you multiply it by thickness, then that will be equal to the storage coefficient. So S, that is the storage coefficient, is equal to H, that is the thickness of the aquifer, times the SS, that is the specific storage. Okay. So another point to consider here is that the changes in the storage volume of an aquifer and the mechanisms relating the changes in pressure head and storage depends on the type of the aquifer, and I will explain in the next slide. Okay, so if you are dealing with unconfined aquifer, okay, so how when you're dealing with unconfined aquifer, a decrease or increase, okay, both are correct here, a decrease in pressure head is basically reflected in lowering the water table. When you say the pressure head decreases, in other words, in unconfined aquifer, basically you're saying the water table lowers, basically. You're lowering the water table. Or an increase in pressure basically means you're raising the water table, okay? So in an unconfined aquifer, a decrease in pressure head is reflected in the lowering of the water table. The amount of water content change is characterized by the specific yield that is presented by SY, defined as the volume of stored water discharged per unit surface area per unit decrease of water table. So that definition, that is the change in the volume, basically, volume of the stored water discharge or taken into per unit surface area per unit decrease of the water table. which is basically the per unit decrease of head, is literally the definition of the storage coefficient. That is the volume of water released from or taken into storage divided by basically per unit surface area per unit decrease in the pressure head. Okay, so the definition is basically the same. So if for the unconfined aquifer, the specific yield will be equal to basically the storage coefficient. Okay. And as a rule of thumb, estimation, typical values of SY for a sedimentary deposits are in the range of like 5 to 35%. Okay, 0.05 to 0.35. So that's just the number that is, so 5 to 35%. That is the typical values for SY. Of course, it depends on the type of the aquifer and other boundary conditions. So here, so here this is unconfined aquifer. You have a water table. This is the impermeable area. So initially the water table, the surface is here, and the unit decline of water table. So the water table, basically you lower it to a new position, and then you can calculate the change in the volume or the volume released or taken from this aquifer by knowing the decline of the water table. Okay. So, but for the confined aquifer, the situation is a bit different. So in confined aquifer, a unit decrease in pressure head is reflected in a lowering of the piezometric surface. But the aquifer, if you remember, the confined aquifer, they are bounded by impermeable layers or confining layers. So the confined aquifers, the aquifer itself remains saturated. Okay, so therefore a unit decrease in pressure head is reflected in the lowering of the piezometric surface. Okay, and since the aquifer remains saturated, the changes in pressure head only results only in small changes in the storage volume. Okay, and in other words, let me read it from this bullet. Basically, in other words, when the hydrostatic pressure decreases, but that is valid for the case of confined aquifer. When the hydrostatic pressure decreases, for example, as a result of pumping water from a well penetrating the aquifer loads. Okay, the aquifer loads to support the weight of the overburden increases, right? Because the water and the aquifer was kind of supporting this the weight of the overburden. So when you take the water, because of the pumping water from when you pump out water, the load on the aquifer increases, and that may compress the aquifer. Okay, and when you compress the aquifer, this may result in forcing some water out. Some water out, basically. Okay, another mechanism that causes taking water out of the confined aquifer as well could be the lowering water pressure. So when you lower the water pressure, this may cause some small expansion and subsequent release of water. But as I have mentioned earlier, the summation, the actual tangible the water extraction is much smaller compared to the unconfined aquifer. As a kind of a rule of thumb or estimation, it's normally you see here. In any case, the storage coefficient for confined aquifer is usually in the range of 5 times 10 to the minus 5 to 5 times 10 to the minus 3, and compare this value with the previous one for unconfined aquifer, which was 5% to 35%. You see it's significantly smaller. Okay. So yeah, basically the whole story is, since the aquifer remains saturated, the change in the water content is small, so you can produce very few water. And the mechanisms by which water comes out, we mentioned here two possible mechanisms. One is that since you're pumping the water out, the aquifer load will increase, and that may compress the aquifer, that sends some water out. Also, lowering the water pressure, okay, that as well may cause some expansion, therefore release of water. And here, what I have explained here schematically are shown in this picture. This is for the case of confined aquifer, as I already, unconfined aquifer, as I already explained here. This is This is a water table at top you have, and then the unit decline of water table basically causes the release of water, and you can calculate it by knowing the depths of the water table, the new depths of the water table, and the storage coefficient and so on, and the area of the aquifer and everything. Okay. But for the confined aquifer, so you have impermeable region here, and then this is the aquifer, that is the saturated area. You see this gray part. Okay, I don't need to. I can delete that one. So this gray area basically is the aquifer, saturated aquifer, and which is bounded at top by a confining layer. Okay, and so you can make this well here, and when the unit basically as I mentioned here, the unit decrease in pressure basically is reflected in lowering of the piezometric surface, and that is what you see here. So piezometric surface was initially here, and now you decrease the pressure, and you are basically the piezometric surface changes, but since the aquifer remains saturated, the release of the water is relatively small compared to is actually significantly smaller than what is expected from unconfined aquifer. And yeah, that basically concludes chapter 2 of our course on groundwater hydrology. I hope you found this video helpful. Thank you.